Okay, so in Unit 6, we've been talking about carbohydrates, and another name for carbohydrates is sugars. So, especially around the holidays, you're probably consuming a lot of carbohydrates, a lot of mashed potatoes, lots of sweets and cakes that are full of carbs, good carbs, but we are going to learn more about carbohydrates in this lecture. What we're going to talk about specifically is what types of carbohydrate linkages are digestible. So we've been talking about monosaccharides, which are they're kind of the building blocks of disaccharides and polysaccharides. So disaccharides and polysaccharides are made up of monosaccharides. The monosaccharides that we saw excuse me, in the last lecture, we saw them in straight chains, and so those are called Fischer projections. They're very useful, Fischer projections, that is, for classifying whether a sugar or monosaccharide is D or L. The problem is when you put these monosaccharides in solution, they no longer exist in the straight chain form. They form rings. So the actual structure of a carbohydrate in solution is called a closed ring or Haworth projection. So remember we saw the monosaccharides being long chains, or just a straight chain like this. I'll make one more carbon. So I'll do D-glucose. You guys can double check me. Hopefully this is the right structure. Okay, so D-glucose, the Fischer projection of D-glucose looks like this. The Haworth projection, or the closed ring structure, how D-glucose looks in solution, is more like this. So you have a closed ring of carbons, and then there are OHs pointing up and down depending on which monosaccharide you're starting off with in the Fischer projection. So this is D-glucose here, the Fischer projection. This ring is the Haworth projection of D-glucose. Now, we don't want you guys to be able to convert the straight chain to the ring form. It's beyond the scope of this course. We don't have enough time to go into that. What we do want you to recognize is whether you have an alpha or a beta monosaccharide based on the Haworth projection. Well, how do you determine if you have an alpha or a beta Haworth projection? Well, you look at the carbon. That's the anomeric carbon. So the anomeric carbon is the carbon that bears two oxygens. And this is on the Haworth projection. So the carbon bearing two oxygens in the Haworth projections, 95% of the time is going to be written pointing towards the right, just because that's how Haworth projections are typically written. So this is the anomeric carbon. It bears two oxygens. Remember, this is a carbon right here. So if the OH off the anomeric carbon is pointing up, you have a beta Haworth projection. If the OH points down, it's alpha. So this Haworth projection is beta D-glucose. And again, we don't want you to worry about converting Fischer projections to Haworth projections. What we want you to do is be able to identify an alpha and a beta isomer from a Haworth projection. So on the next page, I have some examples of alpha and beta Haworth projections. And I want you to circle the beta Haworth projections. So the first step is to identify the anomeric carbon. So the anomeric carbon, remember, is the carbon bearing two oxygens. So if you go through all these carbons, here, 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 you'll end up coming to this carbon. So this is the anomeric carbon. The OH is pointing down. That makes it alpha. So it's not beta, it's alpha. Okay, the other anomeric, this one, this is anomeric. This is anomeric, and this is anomeric. So in the second structure, the OH is pointing up, so this is beta. So there's a beta Haworth projection. The third one, the OH, you might be thrown off by that CH2OH, but the OH pointing down is what matters. So it's which direction the OH is pointing. So this is alpha. And then the last one, the OH on the anomeric carbon is pointing up, so this is beta. So given a Haworth projection, you are to identify whether it's alpha or beta. And the easiest way to do that is to identify the anomeric carbon. And the anomeric carbon is the carbon that bears two oxygens. So we talked about monosaccharides. Monosaccharides in both forms. We've seen the Fischer projections and the Haworth projections. The Fischer projection is the straight chain form that's useful for classifying them as D or L, aldose, ketose, and then how many carbons they have. The Haworth projection is how these carbohydrates actually exist in solution. They exist in the closed ring form or Haworth form. Now we're going to move on to disaccharides. Remember that disaccharides are just two monosaccharides held together. They're held together by a glycosidic bond. So a glycosidic bond is the bond between two monosaccharides. So I have maltose and lactose here. These are disaccharides. You can see that they're made up of monosaccharides. They're held together by a glycosidic bond. This is the glycosidic bond here. What we want you to do is identify the type of glycosidic bond. Glycosidic bonds can either be alpha or beta. And like what we just talked about, it depends on which way the bond is pointing. So with maltose, reading left to right, the glycosidic bond is pointing down. So since this is pointing down, this is an alpha glycosidic bond. Lactose, the glycosidic bond is pointing up. So this is a beta glycosidic bond. Now, you've heard of people being lactose intolerant. So it turns out that there's a specific enzyme that you need to have in order to catalyze the breaking down of lactose. So you need to have lactase. If you don't have lactase, you're lactose intolerant. So you can't cleave that bond because your body does not digest beta glycosidic linkages unless you have lactase. So if you know somebody, or perhaps you are lactose intolerant, you cannot have lactose products. Now there are medications out there that have lactase in them that can help you digest dairy. So it's kind of handy, but as a rule, beta glycosidic linkages are difficult for humans to digest. On the next page, I have another disaccharide, very important disaccharide to me, sucrose, table sugar. Of course, I have a major sweet tooth, and so does my husband, so we're bad for each other in that way. But, growing up in a dentist's house, it was, sweets were hard to come by. So whenever I could get sweets, I was just overjoyed. So table sugar is my friend. Now, table sugar or sucrose can easily be digested. The type of glycosidic linkage, the glycosidic linkage that it has, here's the glycosidic linkage holding the two monosaccharides together. The oxygen off the first monosaccharide is pointing down, so this is an alpha glycosidic linkage. So this is alpha. So easily digestible by humans. Thank goodness. For me, my husband. So that's what you need to know about disaccharides. How to classify the glycosidic linkage. Is it alpha or beta? Now, polysaccharides need to know how to do the same thing. Amylose, amylopectin, and cellulose. These are the polysaccharides that we want you to be familiar with. Amylose and amylopectin are found in starch, so potatoes and corn. So after you've eaten a lot of mashed potatoes for the holidays, perhaps you have a lot of amylose and amylopectin. Now, amylose and amylopectin, this picture is from your textbook. Here is the picture of the first one. A is amylose, and you can see that it's an alpha 1,4 glycosidic linkage, so goes down, so alpha 1,4. And then amylopectin has a lot of alpha 1,4 glycosidic bonds as well, but then every once in a while there's an alpha 1,6 glycosidic bond. So it creates a branching structure. So amylose is alpha 1 to 4 prime glycosidic linkage. Amylopectin has alpha 1 to 4 prime glycosidic plus some alpha 1, 6. So this 1, 6 creates branching. Now, both of these have alpha linkages, amylose and amylopectin. So these are easily digestible. Now, cellulose, on the other hand, this is what cellulose looks like. So cellulose has 1,4 prime linkages, but they're beta. So this is beta 1,4 glycosidic linkages. And a lot of students think, well, cellulose, oh, cellulose, that's, I have a lot of cellulose on my thighs. I'm really trying to, get in shape because I want to get rid of that cellulose. That's not cellulose, that's cellulite. Cellulose is what's found in cotton, paper, vegetables. This is the portion of vegetables or anything that you can't digest. So this is what's kindly referred to, as roughage or fiber because you can't digest it. It goes through your system undigested. So beta glycosidic linkages are not easily digested. So don't get confused and call cellulose cellulite. That's not the same. We'll talk about cellulite coming up with lipids, but cellulose is a polysaccharide that is held together by beta 1 to 4 prime glycosidic linkages. It's not easily digested. So this concludes our section on carbohydrates. So you have a lot to learn in carbohydrates, and this unit's a little different than the other units we've had. It's not heavy in math, it's not heavy really in naming, but there are objectives that you need to master in order to do well on the exam. So please be sure to study Unit 6 material. I want you all to get 100 on this exam, because you can do it. I think of all the units, this is probably the most straightforward one. Low expectations. So study, study, study. Don't blow it off. On the next lecture, we'll start talking about lipids, and hopefully I won't ruin too many of your favorite foods. So do the homework. Study, study, study. Until next time.